It's time to start. There's nothing more to say in the announcement except that we do have six quizzes to work on by Saturday this week. And you know what? Yesterday we just walked through the link state routing algorithm and an example. And you guys also work on another example in terms of a quiz 38. So right at the end, we finish developing the whole link state computation table. Okay, but we have not yet talked about, right, from that table, how we come up with the forwarding table such that the control plane, after finish the link state routing computation, can install that table to the data plane. And this is a very short video telling exactly how we generate the forwarding table.
Just a couple more notes to construct the shortest path to a particular destination from the source. Say from U to Z. Okay, what it needs to do is just to track the predecessor node, okay, and that's trace it all the way back to the source. So Z is the destination. That's traced back from the predecessor of Z, which is indicated here being Y. And who's the predecessor of Y? Yeah, it's stated here, which is V. Who's the predecessor of V? Stated here, W. Who's the predecessor of W? U. That is the source. Yeah, therefore, you see, this is the shortest path from U to Z. The shortest path to X, yeah, indicated by the predecessor, which is U itself. And so we could actually reconstruct the shortest path by just tracing back the predecessors. And you see also here, if we trace back, okay, for all possible destinations to the source, you see also a tree rooted from the source U, okay, to all the destinations. And this is indicating also the shortest path to all the destinations. And such a tree is also called the shortest path tree. And Dijkstra algorithm there is also used to calculate, okay, to generate such a shortest path tree.
All right, so we pause here just a little bit. Okay, so U here is obviously the router doing the computation. Now, if we want to generate the forwarding table such that the destination is Z, what will be the outgoing interface we put there? If you think about it, right, according to the shortest path tree, the shortest path to Z will be going through W, V, Y. So the outgoing interface we put into the forwarding table will be the outgoing interface pointing to router W. Okay. Now for destination being X, then it will be the outgoing interface pointing to router X. If we're setting up the entry for destination V, the outgoing interface will be the interface pointing to the next hub router, W, towards V. Okay, so that's how we generate the forwarding table based on the shortest path tree. And from there, we install to the data plane. Okay, now let me continue playing up the video.
Second note, the D values, okay, when we're picking the I, can have a tie. So in that case, we just have to break the tie and picking one of those.
All right, so when we are doing the link state computation table development, occasionally the minimum big D, there could be 2-3 nodes sharing the same value. Okay, so you just have to break the tie. If it appears in the exam, I will tell you also how we break the tie in case 2 nodes have same D. Okay. Now we are done with distance vector. We are done with this link state routings algorithm, but okay, it works fine. It's not without any issues. There are actually 4 issues. For each issue, we kind of have a remedy for it. Let's go over each of them one by one. First is an issue in terms of performance.
Now with the 2 examples walked through, you see the Dijkstra's algorithm, although look a bit cryptic, the beginning, it's in fact quite straightforward. Initialization phase, 2 steps. Looping phase, 2 steps. Looping phase is the one that we take multiple iterations, we spend more time with. So that is going to bound the complexity of the Dijkstra algorithm. And within the looping phase in each iteration, which of the steps is taking the most time? Yeah, the second step. Inside the second step, we're actually checking all nodes J. Okay, that is adjacent to the node we just added into N prime. And inside each iteration in the inner for loop, what we do is this, the mean operation. And this is in fact to compare the value of the current shortest path to the newly discovered path, right? So D to I plus the link cost between ij. So it's a comparison between this value and this value. So you have the looping phase, and inside there's an inner loop that is doing a lot of these value comparisons. Now, if we consider a fully connected network, that is the worst case for Dijkstra algorithm. Inside the network, there are n nodes. In the first iteration, so only the source is in the n prime. How many j's is connected to the source? Yeah, it's fully connected. Therefore, n minus 1 nodes, they will all be j, and we'll need to do mean for each of these j. First iteration, we'll need to do n minus 1 comparison. Second iteration, how many? Because there's one more node being included into n prime, so number of j in the second iteration, only n minus 2. Third iteration, and we can go on until second last iteration, we have only one node remaining connecting to the new node being added to the n prime. In the last iteration, the second step is not going to be called because there's no j remaining. So if we add all these together, this is the number of comparisons. N multiplying n minus 1 divided by 2. And this is in the scale of n squared, big O n squared. So big O here is actually to say that the Dijkstra algorithm in the worst case runs in the scale of n squared. That means the time complexity, the growing trend of the Dijkstra algorithm is this. When n approach when the network goes really big, the time requirement goes in this trend, like an n squared curve. Now, if it's only big O n, the curve is linear. A straight line, sorry, the line is not very straight here. Now, there's an implementation available for Dijkstra algorithm such that we could do away with only n log n. Now, this is better than n squared. So again, n is here. N squared growing really fast here, and n log n is actually kind of in between. Faster than the pseudocode we've investigated, and better than a linear algorithm. So nice to have an efficient implementation, even though the original Dijkstra algorithm is not so good.
All right, so performance, not so bad. We do have an implementation that can lower the time required to do the computation. Now the second issue, it's called route oscillation.
There's one very special issue with link state routing that's called the path oscillation problem. And it happens when we set the link cost dynamically based on the amount of traffic going on the link at the time. Let me explain using an example. So we have 4 nodes in the example, A, B, C, and D. A is the traffic sink. All traffic goes to A. B, C, D are traffic sources. A generates one portion of the traffic and send it over past BA. E generates E portion of the traffic. E here is a very small amount, much smaller than 1. And C is taking the CBA path to send traffic to A. D generates also one portion of the traffic, and it's taking paths dA to send to destination A. And at this point, we need to update the link cost based on the traffic going on the link. So for link dA, amount of traffic is one portion. For link BA, amount of traffic is what? One portion plus the E portion from C. So total cost, 1 plus E. The cost for link CB, amount of E traffic from C only. You see also here, okay, this direction, BC, there's no traffic, therefore link cost is 0. Similarly for AB, similarly for AD, and similarly here for both direction in link CD. So we finish updating the link cost. After a while, link state routing is going to trigger Dijkstra algorithm running again. Right? As I described, link state routing is a dynamic routing algorithm. We do periodic update, and sometimes we use also network events to trigger recomputation of the routes. Link state routing there does periodic recomputation. Okay? It's going to recompute the routes based on the link cost now. So let's see. B here, we'll see two possible paths to go to A, right? One is to go counterclockwise to A, the other clockwise to A. So this direction here, the cost is what? 1 plus E, because there's only one link and the link cost is 1 plus E. If we take this other path, B, C, D, A, the path cost is the sum of the link costs, 0 plus 0 plus 1. So if we take the clockwise path, to go from B to A, cost is only 1. And this is 1 plus E, therefore B is going to choose to go this way to send traffic to A. C, also see two possible paths. Okay, if we take this direction, cost is E plus 1 plus E, and that is 1 plus 2E. The other direction, cost is 0 plus 1, therefore 1. And therefore, C would choose to go also clockwise to send traffic to A. Similarly, D sees also two paths. This direction here, cost is 1. This direction, 0 plus E plus 2 plus E, 1 plus E. So altogether, 1 plus 2E. So still, this direction better. So D is also going to take the clockwise path, the same path to A. So after the route computation complete, you see B, C, D all change to send traffic clockwise. And then we need to update the link cost again, right? So given the previous cost, we come up with the new routes, and we will then update the link cost, and we come to the new cost again. What is the new cost now? On link BC, there's only one portion of the traffic. On link CD, 1 plus E. On link DA, 2 plus E. And that is why we see 1 plus E, 2 plus E, and all the rest of the links, 0. Once we update the link cost, after the next period that the Dijkstra algorithm is triggered, we compute new routes. So B will then try to see the cost to go this direction and the cost to go the other direction. The cost going counterclockwise is now 0. Cost going clockwise is now 1 plus 1 plus E plus 2 plus E. That's 4 plus 2E. So dominantly, BA is the better path. C's cost going this direction, 0 plus 0, cost is 0. the cos of the other direction, 1 plus e, 2 plus e, 3 plus 2e. So C is going to switch going this direction to send the traffic. What about D? Going this direction, 0 plus 0 plus 0. Going this direction, 2 plus E. So D is going to switch for the first time to go counterclockwise. And that's why in the next moment, you see traffic begin to change direction completely. Okay? From all clockwise, okay, one period before, to counterclockwise the next period. So given these new costs, we calculate the new routes all going counterclockwise, and we update the new costs again based on the traffic. DC is now 1. CB is now 1 plus E. And BA now 2 plus E. And that's what you see here. 1 plus E, and 2 plus E. As a result, BC's this pass costs 0. This pass costs 2 plus E. B switch the other direction. CC's this pass, really high, 3 plus 2E. And this other direction, 0. D, this direction, 0. This direction, super bad, 4 plus 2E. So all of them would switch back like this. And the link cost gets updated again. 1 on this link, 1 plus E on this link, 2 plus E on this link, which is identical to 2 periods before. Okay? And you see the next period is going to be like, yeah, the previous period. And the traffic is going to oscillate infinitely, right? Clockwise, counterclockwise, clockwise, counterclockwise. So that is the pass oscillation problem if we set link cost dynamically in link state routing. Okay, that's running the very straightforward Dijkstra algorithm. Just be careful here.
All right, so that's a really odd case. It did happen before on the internet, but that was when internet was only a baby. Okay, and that is using the amount of traffic on the link as the link cost. Okay, and I see you guys are probably thinking that maybe there'll be other definitions of link cost that would work better and more stable. Yeah, so for example, considering the available bandwidth for the link, right? Or considering delay as the link cost. Using available bandwidth as a link cost, then you probably want to do the longest pass, meaning you want to pass where the cost is the highest. That means the pass gives you the highest available bandwidth. Now, delay, for example, proposed by Chun Mao. That is a very interesting link cost. In fact, for modern days, that might be something that people prefer because we get to send data in shorter delay to the destination. Okay. But the thing is that if you recall in chapter 1, as we are measuring delay, the delay over one link can vary quite a bit as well. To tell you guys the truth, the most common link cost people use is just counting the hops. Okay, so essentially 1 for each link. The link cost for pretty much all the links is 1. So the fewer hops you take, the better. Okay. I think that is generally what most of the networks are configured for the routing. But nowadays, with some networks having software-defined networking installed, there might be some additional settings or more flexible settings. Okay, there might be multiple routing algorithms, multiple link costs, computations being done at the same time. Okay, and then some sort of route integration mechanism there to allow traffic being sent to satisfy different QoS requirements for different applications. So routing with the SDN gets complex. Okay, but as we see also that it can be more general and flexible. Okay, so very good questions you guys are asking there. Okay, this is very tricky. Link cost, defining a link cost before you can do the route computation. And you see also that the computation algorithm is actually the simple, the straightforward thing. Okay. Now let's look into the third issue. Okay, it's not exactly an issue, it's just that we did not say clearly how we get the graph to begin the Dijkstra computation with, right? When we set up a network, okay, a router needs to begin doing the computation, but the assumption is that the router does have the graph, okay, the graph of the entire network there involved, okay, in the computation. So how do we get that?
To put simply, link state routing works this way. Each router implements the routing algorithm. It's going to wait until the total information of the network is in place. Then it calls the Dijkstra algorithm. At the end of the calculation, we get the least cost path from this router to every destination possible in the world. So that is essentially the shortest path tree. That router being the root of the shortest path tree, we'll see there are multiple branches out to the rest of the world. Taking one branch, it gives you the shortest path to a certain set of destinations, another branch to another set of destinations, yet another branch to yet another set of destinations. And so, from the tree structure, okay, we can construct the forwarding table. And that is how the forwarding table is calculated in the control plane. Next is just to install it into the data plane. Now, the only part I'm going really quick without mentioning much is this: how we get the total network information so we could apply the Dijkstra algorithm in the first place. That is done through this link state broadcast. Each node, okay, in the network is going to generate link state report based on very local information. That includes the ID of the node itself, the ID of the immediate neighbors, and the cost, okay, on the link to these immediate neighbors. Okay, so these are the local information. Node, the neighboring nodes, and the link cost to the neighboring nodes. So all these local information is going to be in the link state report coming from the node. This link state report is going to be broadcasted, meaning, okay, going out through the entire network, being received by all other nodes. So all nodes eventually will receive link state reports from every other node. And these link state reports from every other nodes, including the node's local information, is going to be used to restore, okay, the total network. Let me give you an example to illustrate how that is done. We have a very simple network here, only 4 nodes. Okay, you see, U connects to V, U connects to W, U connects to X. Okay, so if we are node U, okay, and generating node U's link state report, it's going to contain this: the ID of the node itself. Yeah, there are 3 neighboring nodes, V, W, X, and the cost on the link to these nodes, 5, 3, 7. So U to V, link cost 5. U to W, link cost 3. U to X, link cost 7. Similarly, V is going to generate its link state report, which is going to contain only one entry. It connects to U, link cost 5. The link state report from W should look like this: 2 neighbors, U and X, cost being 3 and 2. Link state report from X is contained 2 entries, U and W, link cost 7 and 2. So each of these nodes, U, V, W, X, is going to broadcast your link state report, and every node in the network is going to receive its own local information and every other node's link state report. Therefore, node U here is going to receive the link state reports from V, W, and X, which we know already look like this. the way to restore the network topology is this. Okay. Node U knows the local information. It connects to V. It connects to W. It connects to X. Cos is 5, 3, 7. Now, seeing node V's link state report knows that V and U is connected. Cos is 5. V, U, I'm U, so I know. Okay, and the cos is 5. W's report is going to tell, okay, the cos to U is 3, which you already know. Oh, W is also connected to X with link cos 2. So W connect to X link cos 2. X report says I connect to U, so X connect to U, you already know. X reports also that it's connecting to W link cos 2, which you already have. And you now manage to reconstruct the total network information from receiving link state reports from all the nodes in the network. And it's contributing also so that other nodes receiving U's link state reports can also reconstruct the total network. So you see this one here, U connecting to VWX. Yeah, isomorphic, okay, of the network there.
All right. So now you see, before the Dijkstra algorithm can start, there is this link state reports being sent around the network. After every node receive all the reports, graph generated, and then apply the Dijkstra routing. Now the last issue, and question. Good timing here. Is it a good idea to let every router carry out a RTT measurement just like what we do in TCP? Good question. It's a very good question. I don't think that to do RTT measurements in very high frequency is a good thing. But you see that the delay there on a link is changing quite fast, as you guys have observed in the trace route experiments we did in chapter 1. You know what, Yanjun, therefore, as I mentioned, what people more commonly do today is just to set a constant link cost for each link. Because in order to be practical, to really reflect the delay there on a link, you need to do it in high frequency. But that's going to be a lot of measurement that's going on the link. And the link capacity is scarce resource. Okay, we should actually try to strike a balance where most of the bandwidth is for real data, and only a small fraction for control messages like this to try to get an update of what the state of the link is like. Okay, so using that scarce control traffic bandwidth to do high frequency delay measurement, that's probably not a good idea. Okay, so there is a solution to get a delay, but it's not very practical. That's why people still fall back to just set a constant link cost on a link. Yeah, so good call. But if you think about it a little bit more, Yanjun, you see that it might not be practical either. Okay, but generally, fewer number of hops, shorter amount of delay. But this is not very strict. It really depends on the hops. Okay, some hops you do have long delays. Okay, now let's move on to the fourth issue. Okay, for this fourth issue, the remedy is in fact an alternative routing algorithm. So this video is kind of short. Let's go over it.
So that was the last piece of the puzzle, link state routing. Other problems you see here. Now you know a little bit about the link state broadcast. Yeah, some of you might see this. These link state broadcasts, it's going to travel the entire network. And it's coming from every router. Right? So you have n copies of these packets going to n nodes. The bandwidth consumption is again at this scale. And to store the topology information in the router, right? So we discussed the complexity of Dijkstra algorithm. algorithm. We only talk about the time complexity. We have not yet talked about the space complexity. It's also huge, right? In the worst case, you have n nodes fully connected to every other node. Then you have what? N square number of links. I need to store costs, okay, for all these links. Ugh. Not very scalable when the network goes big, when n goes large.
Yeah, so that takes us to this alternative routing mechanism called distance vector. So let me play a very short introduction, and then we'll move on to a series of quizzes, okay? Because this routing, although it sounded really simple, but it's a little bit tricky, not exactly intuitive, although we use it all the time. Okay, here's the short introduction.
So you see, link state routing works fairly well for small networks where n is small. For access network, institutional network, local area network, it might be okay. But for the entire internet's backbone, there's no way we use link state routing. And that takes us to the second routing algorithm, distance vector in the chapter. So distance vector routing is exactly here to address the space complexity, to address the message exchange complexity in link state routing. If you think about it, the reason that the link state routing takes so much space, requires sending of so many messages, is because in order for the extra algorithm to run, we need the total network information. So the question to ask is this: can we come up with a path? Can we discover best paths, best routes without knowing the global information? You know what? It's possible. We just need to be a bit patient though. Okay? So Polly here might have two neighbors, Alice and Bob. Bob and Alice do not know each other. Okay? There's no path existing from Bob to Alice. But if Polly shares how Polly knows Alice to Bob, then Bob will know that there's one way, right, to reach Alice, which is through Polly. So I tell my neighbors, and you tell yours, okay, about what you know. Gradually, okay, the network, okay, will spread the good news out and discovering a path, a route, okay, to every other node in the network. That is the general idea of distance vector.
Okay, so that is actually also called the rumors network routing. Okay, this is exactly how human beings spread rumors. Now let's start from the first quiz in the series. This is number 39. Okay, we do have a small network, 3 routers, X, Y, Z. Okay, and there is a router, a destination far away called W. Okay. Suppose now we are router X. Okay, and you need to send data to W. And what you know is that your distance to Y, one of your neighbor, is 2. The distance to Z, the other neighbor, is 7. Okay, and YZ is 1. Okay, but the thing is this: you don't know how Y and Z connect to W. Okay, what if router Y tells you, "I know a way to W," and Z says, "Hey, I have no idea." Okay, would you pass the data to Y or Z? And why? Okay, good. Yeah, it's a simple. It's probably very simple, right? Based on intuition, you guys will all choose. For example, team 1 here pick Y, right? Because Z has no idea how to reach W. And yet Y says, hey, I know, right? So chances higher that your data reach W if you give it to Y. Very good. So team 12 here, exactly, isn't it? Yeah, because Z doesn't know better. So you give the data to the neighbor that knows better. All right? Yeah, team 4, Wei Yo. Perfect. lower cost toward y. Oh, okay, interesting. So Chunma was saying that, hey, given that we know like the local network, 217, maybe we could do it like xz, y to y, and then y pass it to w. Yeah. So that's something in addition we can consider. But we need to send data to y because obviously z doesn't know. Okay. Let's see. Shu Chen Team 3. Yeah. Y tells, yeah, there's a weight. And z, hey, I don't know. Not a weight at all. Right? Good. Great. So this is quite straightforward. Now, what about this scenario? Okay, this is the next quiz, quiz 40. The network looks exactly the same, okay? But what the neighbors tell you are somewhat different this time. Let's say router Y tells you this: I know a way to W. Router Z also says, oh, I know a way to W now. Okay, and the two of you actually say something slightly different in terms of what they know, the way to W and how it costs. So Y says, I know a way to W, but from me to W, the cost is 2. Z says, I also know a way to W, but from Z to W, the cost is 10. So which way would you choose then? Yeah, so Chunmao's idea, right? Good timing. So I guess for you guys, you probably just calculate a little bit, right? The shortest path to Y is 2. And Y says from itself to W is 2. So 2 plus 2, 4. Shortest path to Z. Oh, interesting. So it could be what? Taking it straightforward, 7 and plus 10. That's long, right? But if you take X, Y, Z to Z, that's 3, right? 3 plus 10, well, that is still long, 13. So obviously, if I am doing it, I will probably still pick router Y because X to Y 2 and Y to W 2, only 4. Yeah, I see you guys. Exactly, right? Y costs the least. Y costs the least. Very good. Let me see if any of you pick something different, someone different. Yeah, I guess many of you picked the shortest one. Yeah. Okay. We will be able to send data to W, and yet shorter amount of delay. Very good. Now, what about 41 here? Quiz 41. Okay, so the information from the neighbors are slightly different. Okay, so this time Y tells X the cost from Y to W is 10. And Z says the cost from Z to W is only 2. Now, would you pass it to Y or Z? Oh, cool. Okay. Team 4, Team 1, Team 12. Okay. So Team 1 here, thinking straightforward. From X to Y, cost is 2. And Y says, hey, cost from Y to W, 10. Then adding the two values together, 12. And Z here, link cost from X to Z, if it's direct link, 7. Okay. And from Z to W, 2. Adding up the 2, 9. Okay. So seemingly, the lower pass is better, right? XZW. But, hey, there's a shorter pass from X to Z, which is XYZ. That's only 3. 3 plus 2, 5, even shorter. Yeah, it's a little bit tricky, isn't it? If you want to make sure that sending data through the shortest pass. But you know what? I think team 1 is perfectly fine. Because in case we don't have enough data to, enough memory space to store a large networks graph. This network we're seeing XYZ, it's a small graph. So we could run something like link state reports and sending these link state reports everywhere, right? The message overhead is not so high. So we could do Dijkstra. And therefore we know from X to Z, in fact, the shortest path is XYZ instead of X directly to Z. What if we don't have Dijkstra routing there? Then information from Z is all we have. And we know there's a cost from X to Z. So team 1 here is actually simulating exactly what distance factor is telling. Okay. Now, team 12, team 4, team 2, 14, you guys. Okay, you guys are thinking this way. You guys are thinking, hey, we are human beings. I actually see the graph. Okay, so we have Dijkstra routing running already. In the meantime, hey, the rest of the network we don't know. So the best we can do is something like what the distance vector is trying to do. Get information and do the best thing we know, okay? To reach someone, we don't see the global information. We don't see the entire graph, okay? Good, so hey, you see that it's a little bit tricky, isn't it? It really depends on the perspective, okay, of the router trying to figure out a way to the destination. So team 1 has a perspective, no Dijkstra routing at all. The rest of you guys, kind of assume there's Dijkstra routing there. So you know XYZ is in fact the shortest path, isn't it? All right. Yeah, so you see here, team 14 says XYZW, the exact path, XYZW. So what's a little bit tricky in this quiz is also this. If we pass data to Y, would Y pass it down to Z and then W, or Y directly to W? This actually tells you a little bit of the trouble we are running into on the internet. This is actually simulating what the internet is working. Within the local area network, we do something like Dijkstra because a local network is smaller. It's actually more manageable to run Dijkstra, to run link state routing. But to connect from local area network to other local area network, because internet is what? A network of local networks. Okay. At the higher level, we do distance vector routing. We do this rumor network routing. Okay. And there will be some hooks between local routing to the higher level global routing. All right, but I can tell that you guys know very well what is the optimal path, okay? But later on next week, let's learn how we hook the local routing to the higher level routing, all right? But what I want to make a point with is this, okay? This is quiz 42. This second flavor of routing, okay, is not really something that we can optimize exactly. Okay, it's unlike a link state that we could try to calculate for a shortest path. Okay, we don't know at any given point in time whether we are really sending data through a shortest path. We are just trying to do best effort. Okay, given what we know. Okay, given the perspective, okay, we have, okay. So if we are at a different perspective, the perception can be very different. So the best router X is seeing may be very different from what the best router Y is seeing, okay. So quiz 42 is asking this, okay. For Q1, I think it's very simple, okay. Although I did not upload the images yet, okay, I just uploaded the images now. For Q1, okay, Let me ask you what I'm showing there. I think Team 4 is already saying something. No, not yet. Okay, so Team 4 deleted the answer. So what is that? What is that? As human beings, we see the whole picture. We know it's an elephant. Right. But look at all these guys being blindfolded and trying to discover what that is, right? So the guy in the front touched the what was it, the tooth? I think that was musk. I forgot exactly the term for it. It's pointy. So the guy says it's a spear, right? And the guy at the top, okay, feeling the elephant, but okay, the guy actually feel the ears of the elephant. So it's flappy, soft, right? So it feels like a fan, right? The guy at the tail, okay, thought that, hey, this is a robe. So if you're blindfolded somehow and then try to discover something, okay, you have different perspectives. Therefore, the perception very different. In distance vector routing, this is exactly how the router is gonna be feeling like. All right, and then we move to the second part of quiz 42. So I'm trying to find how I show the PowerPoint. There we are. All right. Okay. Okay. All right. Now, Q2. Okay, I'm gonna reveal hints one by one, and you guess what the mysterious object is there. Okay, what the question mark is. Okay. So, okay, the first subject, hold it, and she discovered that you can drink it. So it's a drink. The second guy says, oh, okay, it's cold. Okay. And then 3 more subjects test it and drink the beverage. Okay, so the girl on the left says, oh, sweet, soft, and chewy. Okay. All right. There you go.
Just a couple.
Sorry. This is actually more what I want to go to. Yeah. So with those hints, you gradually know more. So this is also how a distance vector router feels like, because these distance vector routers, they will take whatever they know the best, okay, and think again. Okay. If they feel, oh, okay, there's something else. The best information I know is no longer the best. With this information, the next period in time from one of the neighbor, I see something even better. Then I will renew my knowledge, and then I will spread that, okay, to the neighbors further. Okay. Yeah, so that's why the rumors gets elaborated and elaborated and elaborated. Okay, so I see you guys. Yeah, chewy beverage, of course. Bubble milk tea. Bubble tea. Okay, yeah. It is chewy, definitely. Yeah. Which beverage is chewy? You know what? You guys are very, very correct. Okay, so bubble tea is also one of Polly's favorite beverage. Oopsie. There you go. Sweet, soft, and chewy. Okay. Tusk. Thank you, Tian. Tusk. All right. All right. I hope the series of quizzes, okay, make the point I tried to make, because distance vector is a very curious mechanism. Okay. You don't get the optimum right there at once. You gradually discover, and you get closer and closer to the best route. Okay. And this is a great time to take a break. Let's break and come back to talk about distance vector. Okay. There's also an algorithm for it. Okay. All right, so break. And of course, I will come back to address the questions from Shu Quan and Celia after the break.
Hi, Polly.
Hi, Yanjun.
I was wondering.
Hmm.
Oh, I hear my echo. Okay.
So you probably want to mute the YouTube stream.
Okay. So the question is, you just mentioned that in most cases we use the number of hops as the cost, the link cost, right? And I was just wondering that would it like making the conjunction worse because like when a certain path there are many packets there, but the cost doesn't increase, right? So people would going to use that path more,
Right, right, right,
and then things will get worse.
right, right. It does. It does. That's why we need software-defined networking. Um, so previously, okay, or as I described, commonly people just take the shortest path, which is in terms of hops. Okay,
Yes.
and chances high that people take the same path. And so traffic volume there will be very high.
Yeah.
So how do you balance load? Um, uh, Previously, what people do is more this. Okay, so traffic coming from you, there's probably a major router here at your ISP, at your local ISP. Okay, and this local ISP typically knows multiple ways going to the destination. Okay, so that ISP might do with the router there is to send packets, okay, in a rotating way. So
Oh.
some packets go this way, some packets go that way. That is also why in some of the trace route experiments we did earlier, we see, hey, packets do not necessarily go through the same route, same router. For example, in hop 7, you might see two routers, okay, for the 3 packets.
Uh-huh. Yeah, I remember.
Yeah, yeah. So that's the tricks that people typically do nowadays. And that is regardless of having SDN or not. Now, with more networks having SDN there, what they can do is even better because you can do generalized forwarding. So you could have flows coming from a particular source going this way, flows coming from yet another source going the other way. Okay, that way you get to make sure that the packets actually traverse the same way. Usually the delay is a little bit more stable. So it is a little bit better with the generalized forwarding, provided SDN being available for that network. It will be actually a little bit more. It would actually serve streaming applications better. You see video audio
Uh-huh.
streams, you do need short delay, of course,
Yeah.
but in case you don't get short delay, it will be better if the delay is longer, but all the packets come in consistent delay. So for example, live stream now, some of you are actually a little bit behind and some of you a little bit ahead. And those that are behind is because that the network is probably seeing that the client is probably seeing the delay coming from the source is not exactly very stable. So it would actually delay the playback such that the packets can continuously come in and play back at the right time instead of you missing many of the frames. You see, the client can play fast, but the client might miss many of the frames. So the video might look a little bit sort of flaky or
Uh-huh.
well, how do you describe that? Okay, so we call it like a frozen effect, but it's not exactly frozen. You see that the reaction time, rendering the frames are really low, so it's actually very uncomfortable. People usually cannot stand watching that kind of video a long
Uh-huh.
time.
Yeah, I think I get your meaning.
Okay, good, good. Yeah, so so currently, I think for mass majority of the edge networks, there's not yet SDN. They do this kind of round robin maybe forwarding. And that is perfectly fine for example, file uploads.
Okay.
For streaming, it's a little bit troublesome. Yeah.
But that means we're not necessarily taking the optimal path, right?
No, we are often not taking the optimal path. We are more, in fact, not taking optimal paths. You're right. Sending data from within, for example, within NTU though, it's more or less optimal because each link delay short and there's not much traffic. Relative to internet backbone, not much traffic and short. And I think we are running OSPF within NTU. The NTU network actually not many hubs. Okay, so it's very simple, in fact, in a local area network, even though routing is necessary. Okay, what's complicated is after we go out of NTU. You will hear more next week about the inter-domain routing. So Dijkstra or link state routing is used usually within a local area network. It's called the intra-network routing, inside network routing. To connect in between network, inter-network, we use distance vector because this inter-network is huge. Internet is huge. Even though that we already have we are doing it at the second hierarchy, right? It's not like connecting individual routers. No, it's not like that. But the number of networks out there is still high. Okay, so we use distance vector type of routing instead at that higher level.
Okay, so it may sound weird, but if we are not taking the optimal path, is this like necessary for us to know how to find it?
Exactly. Well, but you see, I mean, you could random walk. Random walk then is not good because you can have ghost packets on the internet forever with certain probability. Yeah. So I think to do completely random, not good either. Optimum is not possible.
Okay.
So distance vector there is just trying to do better if there is better information.
Okay.
Best effort.
So then we will have the path to be among one of the best.
Yeah. It's close, but sometimes not perfect.
Okay, I see.
All right, good.
Thank you.
You're welcome. All right, and we should really come back to the lecture. So let me just play a very short video to tell you again the spirit of distance vector routing.
That should give you a rough sense how a router discovers a route without seeing the entire network topology. That is asking the neighbors to help. So neighbors will be reporting how they know about the destination. Now you know the neighbor's cost to the destination, and you know the cost for you to reach each of your neighbor. So that be X, and the cost from the neighbor to destination Y. You can calculate the sum of X and Y. If the value here is not infinity, you've discovered a route to the destination. But in order to discover the route that is the best to the destination, then you will need to check through all neighbors. Okay, for each neighbor, you find the cost to each of these neighbors. And you find out from that particular neighbor the cost to the destination. And you sum up, okay, X and Y for that particular neighbor. So you pick I such that Xi plus Yi is the lowest. There, you discover the best route, the shortest path. And I there is the next hub that leads to the shortest path to the destination.
All right. Okay, I just realized that I neglected the questions on the chat. Okay, so let me Let me see. Shu Quan was asking, what about run a breadth first search or depth first search first? Then we have the global information about the cost. You know what? Yeah, Su Quan, you probably know better now. How come we don't get the global information? Therefore, there's no graph we could do BFS or DFS to begin with at the first place. Okay. If we do have the graph, right, and you can definitely try BFS or DFS instead of doing Dijkstra. Okay. Celia was asking about the music, and Chunma was saying, okay, there exists a special bottle we can drink bubble tea without straw. Oh yeah, okay, yeah, definitely, yeah, Celia, good point, right? How do you know it's chewy if you are if you are not using a straw? Yeah, okay. Okay, so that was regarding the Q2 of quiz 42. Okay, good. Next segment of videos, we'll begin to introduce the algorithm. Okay, so the algorithm, including introduction of this equation called Bellman-4, total will be about 10 minutes long. All right, so I guess you guys all have fun with the quizzes, and you guys are now curious about internet routing. But let's focus for the next 10 minutes and get to see the exact algorithm of distance vector routing. And first, let me introduce the Bellman-4 equation.
You see right on the slide that what I was describing is exactly how distance vector algorithm works. So let me define the term here. dxy is the cost, okay, of the shortest path to go from x to y. And so what we're calculating here is the minimum cost to go from x to y, or to discover the shortest path from x to y. The way to do it is to go over all the v's. Okay? V's are the neighbors of the source. For each v, we calculate the cost to go from the source to the neighbor, plus the cost from the neighbor to the destination. So the sum here is the cost to go from the source to the destination through a particular neighbor v. So all we need to do is just to go over all the neighbors and calculate the sum for each neighbor and pick the neighbor that gives us the minimum value. And that minimum value is the minimum cost, okay, from x to y. And that v there is the next hop along the shortest path to the destination. So by doing this calculation here, we discover the shortest path. We discover the minimum cost. And this equation here is better known as the Bellman-4 equation, because this algorithm implemented in distance vector routing is devised by these two great guys. Let's try to exercise the Bellman-4 equation using an example. And let's calculate the shortest path from U to Z. Right? Our first thing to do is, hey, we need to have the neighbors, right, reporting, okay, how they know about the destination. So use neighbor including V, W, and X. So V will need to report the distance from V to Z, and that is the entry here. X will have to report the shortest distance from X to Z. Same for W to report the shortest distance from W to Z. And then we can begin, okay, doing the calculation. So we'll be going through all three neighbors one by one. So let's take the first neighbor V. Okay, so link cost from the source to V is 2. And dVz is 5. So we have 2 plus 5 here. Okay. From U to Z through V, the cost is 7. Second neighbor, X. So this is the second one. Link cost, okay, from the source to X, 1. And dxz reported as 3. So this is 4 here. Wow, nice. Third neighbor, W. link cost is 5. And DWZ 3. So together 8. So obviously 4 is the minimum value. This is the minimum cost from U to Z. And you know what? X is the neighbor that gives you the minimum cost. Therefore, X is the next hop leading to the shortest path. So here, X here, achieving the minimum is the next hop in the shortest path. And that is also, okay, the link pointing to X is the link interface to insert in the forwarding table for destination Z. So that was the Bellman-Ford equation, which captures nicely how one discovered the shortest path, the minimum cost to go from the source to the destination. But you see also in the previous example, right? Calculation of the Bellman-Ford is actually based on these information. Cij, okay, the link cost from the source to each of the neighbors. And these, the shortest distance from each of the neighbors to the final destination. Alright. That is also saying the distance vector algorithm as a whole contains the Bellman-Ford algorithm. But before the Bellman-Ford can be calculated, each node will also need to collect these information. Now, this is actually configured in from the network admin when the network is established. Now, this actually relies on the neighbors, okay, sending their routing information to the node. Okay, so next, what I'll be talking about is to go over the entire distance vector routing algorithm, covering both the message passing part as well as the Bellman-Ford part. Now, before I talk about the entire distance vector routing algorithm, let me introduce just one more notation. dxy is the shortest distance from x to y. This is not new. The new one is here. A node is going to maintain the shortest distance from itself to every possible destination existing in the network. So, capital N here is the set of the nodes in the network. So we do have multiple values of these dxy, okay, because there are multiple values of these y's. So each of these values is the distance, the shortest distance to a destination in the network. Therefore, we call this a distance vector. It's denoted as capital D. Now, because this is the distance vector for node x, therefore it's called the dx. Good. So the distance vector routing algorithm, the goal is to derive dx for each node x, right? And before we could calculate dx, okay, the node here needs to have two pieces of information. Okay, according to the Bellman-Ford equation, we need to know the link cost from the node to each of the neighbors. So CXVs. Now, in order to have the shortest distance from each of the neighbors to a particular destination, yes, we need to also know, okay, the neighbors' distance vectors. So for each V, node X here also maintain dV. And now the algorithm of distance vector. You see here, a key idea is it works in two phases. First of all, each node sends its own distance vector to the neighbors. So this is the message passing phase. And then two. When the node receives the distance vectors from all the neighbors, Bellman-Ford equation calculation begins. And as a result, okay, the node x there discover its own distance vector. And we could loop back. Okay, this node here then will pass the dx to the neighbors. That is the general idea of distance vector routing algorithm. The Bellman-Ford equation, now this is the Bellman-Ford equation. Okay, know that when x receives all these dv's from the neighbors, dx is not just one value to one particular destination. So this Bellman-Ford equation is going to be called, again, these many times, so that we derive the shortest distance to each of the possible destinations in the network N. Right. Yeah, final note here. Under minor natural condition, the shortest distance from X to Y, at the beginning, it might be really, really bad, okay? But as time goes by, it's going to converge to the actual least cost. So, minor natural conditions means that, for normal internet operation, this is going to hold true. To be more precise, this is distance vector routing algorithm, and it's depicted such that it looks like it's working in cycles. Each router in the network operates such a cycle. First, it's going to wait for one of these two events. Very common is that you receive a distance vector from the neighbor. Occasionally, this router here might detect there's a link cost change among these links to the neighboring routers, because these two events might affect the result of the Bellman-4 calculation. So these two events occur, we trigger Bellman-4 calculation to begin. As a result, we get a new distance vector. Now, if the distance to any of the destination has changed, that means, better route discovered, shorter distance discovered. Then we tell to the neighbors, because the neighbors might also benefit from the good news, benefit from the discovery. So you see, distance vector routing algorithm working this way, it's iterative, meaning it works in cycle. In each cycle, it can only be triggered by two kinds of events, link cost change and DV update messages arriving at the router. It's also distributed because one can calculate and discover a better route and pass it to another node. So each node notifies neighbors of a better route, and the neighbors then calculates even better route and notifies the neighbors. So in the end, they converge to the shortest path, but the effort is actually shared, distributed, and contributed by all the routers in the network.
How do you like this routing algorithm? It is certainly interesting, isn't it? Okay, so let's take a look at the concrete example that usually helps.
Okay, example time. In order to make sure that you understand this thing clearly, let's use a concrete example. So the example this time, very simple, only 3 nodes, X, Y, Z, and they are fully connected. Oh, by the way, we have not yet talked about initialization of the distance vectors. In node X, the distance vector of X is initialized this way. For destination X, well, it's itself, therefore, distance 0, it does not cost anything to transfer data from X to X. To go from X to Y, let's initialize it to the link cost of XY if they are adjacent to each other. So, to here. XZ, so XZ, they're adjacent, therefore we use the link cost between XZ. Similarly, you do the same thing to initialize dy for node y, dz for node z. Now, in node x, it maintains all neighbors' distance vector, alright, but at the initialization phase, node x did not receive anything from y nor from z yet, so dy and dz, these two vectors, are left null. So I'm just using the sign of infinity there, to represent their null. Similarly, for dx and dz in node y, and so on and so forth. So this is how you initialize the initial distance vector table, which is composed of 3 vectors. You maintain your own vector, you maintain also the neighbor's vector. Once, the vectors are initialized, each router will what? Notify the neighbors. So this vector here will be sent from X to all the neighbors, X to all the neighbors, y, and z. Similarly, no y is going to send its initial table to x and z. And similarly, z sent to y and x. Right. And that's why, okay, in the next cycle, no x here in the table, it's going to see dy from no y, dz here from no z. Now, with neighbors distance vector in place, now we can begin to calculate dx. So what is the value of dxy? What is the value of dxz? Now let's start from calculating dxy. Right? So the Bellman-Ford equation says we try through all the neighbors, okay, of the source. X is right here, the source, two neighbors, y and z. So yeah, we do have two entries here. Okay, one is assuming neighbor being y. Second, using neighbor z. So, okay, for the first sum, we use the link cost from the source to first neighbor, and then adding the shortest distance from the neighbor to the destination. Now, in this case, neighbor happens to be the destination, so this is 0, okay, as dy y says 0. Link cos xy, 2. So 2 here. Now for the second neighbor, z. Link cos of xz, 7. So 7 right here. Shortest distance from neighbor z to destination y. Okay, then we need to look up the table. From z to y. Right here, it says 1. So 7 plus 1. This is 8. And this is 2 only. Therefore, y here wins. Okay, y is the next hop router, okay, to y. So therefore, we write 2 right here, okay, for x, y. And now we derive dxz. Okay, so from x to z. Again, from the same source, two possible neighbors. One is y, the other is z. Link cost from x to y, 2. So 2 right here. Shortest distance from y to z, we'll have to look up the y row here to z. So the distance vector from the neighbor y suggests it should be 1. That's what we are seeing here. Now for the second neighbor z, link cost from x to z, 7. So 7 here. Shortest distance from neighbor z to z, trivial. And yeah, it should be 0 here in the table. So this is 7 and this is 3. Therefore, y wins again. To go from x to z, take this path. And we can add 3 back to the distance vector of x. And what do we do next? Yeah, now x here acquired the new distance vector. It's going to what? Send it to all the neighbors. Okay. So this is the first cycle, calculating the dx, okay, from the x's point of view. Similarly, no y there is going to be calculating the dy. No z there is going to be calculating the dz because it's receiving dx and dy.
And that's exactly what we will do for quiz 43. Let's calculate dz, okay, which is this. Okay, so we just finished calculating dx, right? So we get 0, 2, 3 there as dx. Now let's calculate dz. Okay, you guys have 10 minutes time to do the calculation. So Okay, so it does look like 10 minutes is too long. All right, good. I see you guys got it. Yeah, so for DZX, okay, so consider two neighbors, right? In case of Z, neighbors are X and Y. Okay, so Z to X is 7, so the first link cost. Yeah, so first link cost. So maybe I look at Jessica. Yeah, this is very detailed. Great, love it. Okay, so help me explain also. Okay, so let's look at Jessica's solution here. Yeah, this is Bellman-4 equation, isn't it? Consider two neighbors. In Z's case, neighbor X and neighbor Y. Cost to neighbor X, 7. XX, 0. Cost to Y, let's see, cost to Y, from Z to Y, 1. There we go. And DYX, so YX, 2. Look up the table, right? 2. Good. So DZX gets 3. And DZY, let me just not go through the detail, gets 1. Did you guys also get it the same thing? Yeah, Shuquan also 310. Chunmao here, prefer writing? Yes, exactly, 310. There you go, Sheng Wei and Yinqi and Lawrence. Same for Zoe. Okay, love it. Yeah. Very good. You've got it. Okay. So let me just play the rest of developing the tables in this scenario, because what we're doing is just to check what is the dy in the first cycle. You also need to do what? To do dy in the first cycle. And afterwards, if you observe dx, the entry dx, small dx, changed. Calculating z's table, dz also changed. So in that case, what do? Oh, we need to propagate the distance vector further to the neighbors, isn't it? So the next two videos is just to show you how all the computations are done until the network converge to the shortest path, and there's no more distance vectors being passed around and triggering more computation. So we will reach a convergence state where everyone gets the shortest path and no more message and stable. Okay.
Let's try to calculate the distance vector of Z together. So you see, it will be the shortest distance from Z to every possible destination in the network. And in the network, it's very small. Starting from Z, there are only two possible destinations, X and Y. So we just need to calculate DZX and DZY. Now let's calculate DZX first. According to Bellman-4 equation, okay, so what we do is to try to find out, okay, through all these neighbors connected to the source, okay, which one leads us to the shortest path to the destination X. Now, in this network, we do have two neighbors, okay, connected to Z. So let's try the first neighbor first, which is Z. So we'll be using the link cost from the source to the neighbor. So link cost from source to neighbor, Z to X being 7. And then based on what the neighbor knows, okay, the shortest distance to the destination. In this case, neighbor is X, destination is also X. Now we look up the table. So dx here being known to Z, according to that, dxx is 0. Now the second entry, the second neighbor is Y. And so we'll then take link cost from Z to Y, which is 1. And then based on Y knows the best to the destination X. So dyx, okay, is the value we need to add
link costs zy2. And according to the table, okay, dy says dyx being 2, therefore 1 plus 2. So going through x, we get a pass. The cost is 7. Going through y, we get a pass that the cost is only 3. Therefore, 3 wings. Okay, so you see here, to go from z to x, the shortest pass distance is 3. And the next hop is obviously y. Let's calculate the other entry, which is zy. Let me clear the markup first. All right. Okay. Again, according to the Bellman-Ford equation, source is z, and the destination we wish to find out the shortest pass cost is y. Yeah. In the Bellman-Ford, we'll try, right, for 2 different neighbors in this network of z and see which lead us to the shortest pass. So let's try the first neighbor here, x. Link cost being 7 again, and then what about dxy? Now let's look up the table. It's dxy, therefore the shortest distance is 2, so we ended up adding 7 to 2, which is not, doesn't look so good. What about the other neighbor of z? zy is 1 again. What about the shortest distance from y to y? And hey, it's itself, so y to y, the cost is 0. So this other pass going through y give us only pass cost 1, therefore going through y, this gives us the shortest pass from z to y, and therefore we update the entire dv, which is now 310. We can actually continue and calculate what is dy, isn't it? So there are again 2 entries, yx and yz. Let's calculate yx first. Okay, this time y is the source and destination is x. Again, we need to try through all the neighbors of y. So let's start from x. So x in the middle, source being y, destination being x. So we go through link yx, which is 2 here, and then find out what is the shortest distance from neighbor x to the destination x. So neighbor and destination happen to be the same node. According to the table, x, the value is 0. So here, going through neighbor x, ooh, nice. Total cost is 2. The other neighbor, so y's other neighbor is what? Z. So z in the middle here. Link cost yz, 1. What about the shortest distance z knows to the destination x? So dzx, we'll have to look up the table here. dzx, which says 7. So the best path, okay, going through neighbor z is unfortunately, costing us 8. So comparing the two, the path going through neighbor x is better. Okay, so yx and then reaching x. So total cost 2. So we can now update, dyx to 2. The second entry in the distance vector of y is dyz. Okay, so again, starting from y, going to the final destination z. So starting from y, and this time final destination z. We'll have to try through both neighbors. First neighbor being x, link cost from y to neighbor x is 2. The shortest distance from x to the final destination z, dxz. So let's see, dxz. The entry in the table says 7. Second neighbor being z here, so yz, the link cost is 1. Nice. What about the shortest path from z to the final destination z? Yeah, it's actually quite straightforward, isn't it? ZZ, trivially 0. And 9 comparing to 1, which one is shorter? 1 here. At this point, we can also update the entry dyz. And this is how we come to the distance vector of y. So we now finish deriving all the distance vector tables at time t1. What you see also is this. Look at this. dy and dy, okay? Between t0 and t1, dy did not change. Therefore, dy here, no y here, does not need to propagate the data, okay? Propagate the vector to no x and no z. While, okay, when x here finds out the dx, which is different, okay, from t0's dx, we'll need to propagate dx to no y as well as no z to calculate the table for t2. Similarly here, z find out the new dz being different from the old dz, we'll need to propagate also dz to no x and no y. Therefore, the two other nodes can calculate if the dx and dy needs to be changed further.
So after the quiz, you'll see dx is changed and dz changed as well. So no x and no z will be propagating, okay, the newly discovered, the better distance vector, like this. So no x receiving the update is going to replace this with the new distance vector. Just like y here, okay, this vector here is going to be also replaced with the new vector from z. Similarly, this vector here is going to reach z, and z is going to update from 0 to 7 to 0 to 3. Now, what's a bit special is this, okay? In the quiz, you see that dy here at no y is actually not changed. Therefore, no y here is not going to distribute to 0, 1, okay, to x nor to z. So this stays the same. Therefore, this and this stays the same. But no y here is going to receive a new dx and new dz, therefore this gets changed to 0, 2, 3. This gets changed to 3, 1, 0. You see that in cycle number 2, x, y, and z, they actually converge. Okay? The view is consistent, and they all converge to the shortest path, okay? The least cost path. So in this very simple example, we see distance vector using the Bellman-4 equation works really well. Converges in 2 cycles.
All right, so that was a full example of distance vector. We do have several questions here. Maybe we could address these instead of go on with the issues with distance vector. So coming next Wednesday, we'll continue on and talk about distance vector routing, but just like link state routing. So after we talk about the algorithm and give you an example, we talk about the issues. Okay, so there are some issues with the routing algorithms. Link state have 4. Distance vector also has an issue, which is quite a headache. You will see. And the way distance vector work is in fact a little bit asynchronous. So one of the questions I see you guys ask is actually related to the issues in distance vector, and we'll learn about those next week. Okay, so let me go through the questions first. Okay, I think okay, so Yanjun was asking as we are walking through the example, right? So no x there as x is recalculating for dx. Okay, it finds the shortest distance, but yes, dx also remember exactly which neighbor gives the shortest distance. Okay, so exactly Yanjun. alternative paths are those neighbors with maybe slightly higher costs. Yeah. So you see that there are multiple neighbors, and these are all potentially alternative paths. Okay. And yeah, Qing was asking. Okay, so in this example, because we have a very small network, only 3 nodes, and everyone else's neighbor. Okay, so in the data we keep for distance vector routing, we have the distance vector for the router itself. We have distance vector for the other 2 nodes. Okay, does that mean that we keep the distance vector from all the nodes in the network? No, we only keep the distance vectors from the neighbors. Okay, only the distance vectors of the neighbors. So that way, the amount of memory required to do distance vector routing is more scalable, right? We only keep it for the neighbors, not the entire network. That's in fact the whole point of doing distance vector. We don't need to know every other node on the network. Yeah, so Ian Jun is asking a very, very good question next. Will the async updates between routers kind of leave outdated information in the network? You know what? It does, but it happens in some cases. Okay, not all the time. Okay, so if there is a change in the link cost, or if there is a node being added, or things like that, it really depends on what the change is. Okay, so if the link cost is lower than previous, than what they are previously, so if it's good news, because lower link cost means shorter path. Okay, the way Bellman-4 work is that we take the one with the minimum cost with the shorter path, so we will be able to learn shorter paths fast and propagate. Okay, but for longer paths, we probably don't keep that information. Okay, so you can probably imagine a little bit that if the link cost is suddenly bad, that information does not get propagated. In a way, the link is changed, but the latest information did not get propagated. Okay, all those better paths involving this link will stay there for a while because the new cost is worse than the cost of the link previously. So this is rumor network is exactly this, right? If rumor is finally being cleared, okay, it's the information being spread is false. It usually also take a long time, and sometimes the correction never reach all the audience. Okay, because the receivers of the information earlier had already a strong impression of it. Okay. Yeah, so the clarification might not really reach all. That's the power of the rumor network, but that is also the disadvantage of the rumor network. Okay, it's a little bit hard sometimes to try to make corrections. Yuqi was saying numbers seem wrong. It's probably in the derivation. So Yuqi, if you, I understand that I probably make some mistakes in the animations on the slide. So feel free to point out exactly where. Then I would appreciate and try to make changes afterwards. So I think Yan Jun is responding. Oh, I see. The old information will be overwritten. Yeah, so if the link changes, change to a better link cost, then it gets quickly overwritten. But if the link cost is worse, it will take time. But it will still be changed, but it will take time. There is actually another way, a special mechanism in distance vector to try to make sure that the link cost change to something that's worse than previously, to ensure that gets updated faster. That's called the poisoned reverse. Okay. The textbook mentioned poison reverse, but never really talk about the detail. Given the time constraint, you know what, guys? We have just 1 week of lectures left. Okay, I have not yet talked about how the link state routing in the local area network works and how distance vector works at the higher level, connecting the networks, and how intra-AS routing, intra-network routing, and inter-network routing interact. Okay, so next week, we'll definitely try to wrap up distance vector and then go there. Okay, talk about how really routing algorithms are embedded or included in a official routing protocol, okay, and runs locally on a network or runs globally at the higher level of the internet, okay, that higher network of the local networks. Let me see. Yuxiang, would the converge table be the same with Dijkstra's answer? I think so. If there's no change on the network, the end is always also shortest path. To prove it, I think it will be harder. For Dijkstra, I try to do proof, but I kind of talk through the proof. If you include a node, not yet in n prime, but we take with the minimum d, that will actually always give you the shortest path tree. So Dijkstra is much easier to prove because it's centralized and you have global information. But for this, it's a little bit harder. I can look if there's a proof, but I can imagine the proof is probably very long because it's a distributed system, usually very hard to prove. But Yuxiang, very good question. 博智, so does convergence mean the metric to metrical symmetry? Yes, that's very good observation, 博智. You do see that metric, right? dx, dy, dz, when it converges, it's symmetric. It is. I think so, but I'm actually not quite sure, giving it another thought. Would it? I think so. I think so. But again, I cannot prove. Intuition says so. All right. Hey, it's past the lecture time, so let's call it a day and go off and grab lunch. Now, feel free also to stay on because the next hour is the office hour. So if you have further questions, feel free to type them up on the chat and let me know. All right, so let me resume. This is Brahms, Symphony No. 2 from Berlin Philharmonic. And this is the last movement already. Yeah, bye. Go. Okay, bye guys.